All right, I'm doing Monte Carlo localization. So localization is the process of determining a robot's position or orientation in an environment. Monte Carlo localization is a probabilistic method to do that, which uses a set of particles that represent possible positions, and then over time, based on movement commands from a robot and sensor readings, those position particles are updated. So it's designed to work in environments where an agent doesn't have knowledge of the exact map or position, which is kind of the open world assumption. The goal of MCL is to estimate the true position of a robot over time. So each particle represents a possible position, and as the robot moves, the particles adjust and get resampled to track onto the true position, which you can kind of see going on down here. This is from the textbook. It's effective in environments with uncertainty, where your sensor could be noisy or your movement data could be noisy. So this is the textbook approach. Over here on the right is the actual pseudocode code, and then on the left is kind of the high-level overview of what's going on. So I'll go through these more in depth. So the first step is initialization, where the particles are distributed randomly over the scene right here. And then after that, on each iteration, the particles are moved based on the robot's motion model. So here, if my robot movement is passed in as 10 to the right and 10 up, we're sampling from that to get some kind of noisy simulation in the data. But the particles know roughly how much the robot is moving. This min-max stuff here is so it doesn't go out of bounds. And then after that, there's a correction step. So particles are weighted based on the sensor readings. So here, you take in a particle and then the true position of a robot, which is kind of our sensor simulation here. So I'm finding the Euclidean distance from that particle to the sensor, and then there's some noise applied to it to make it more realistic. But this is basically a distance function, which is our weight. And then we resample, so particles with higher weights are more likely to be included in the next iteration. So over time, due to these normal distributions, we're getting points that are more and more close to the true position of our robot or agent. So here's how my kind of simulation loop lines up with the pseudocode. So you can see the main things in here. Most of the other stuff is just matplotlib or me moving my agent. But yeah, this is how things line up. I'm not doing the ray casting because that involves like a complex scene and ray tracing, which I didn't have time to set up. So you can see over time, this is our red is our true position of our agent, and then with each iteration, the particles, which is the estimated position, cluster closer and closer, and are estimating more accurately, even though you can see the agent is moving from step to step. So testing is a little hard because the algorithm's not deterministic. There's a lot of noise and sampling going on, but the main idea was to observe that my particle, the particles were converging towards the agent. And then there's some differences I wanted to touch, but I'm out of time.